just like ideals can be generated by a single element, or, as we saw at least once, multiple elements, we're going to talk about how we might generate subgroups by picking out elements of the group. So let me give you an example to say what I mean here. I'm going to consider the group Z6 under addition, and I'm going to start by taking one element and seeing what else needs to be in the set that it generates to make sure that we're going to end up with a group. So if we start our set with 2 mod 6, my group needs to be closed under addition, which means I need to add 2 to itself, and then I'll get 4 mod 6. And then I need to add 2 to 4, and I get 6 mod 6 or 0 mod 6. And I continue adding 2, but I see that I keep getting these elements back. And then I need to ask myself, is it non-empty? Sure, it's got 3 things in it. Does it have an identity? Yep, it's got the additive identity 0 mod 6. Does every element have an inverse? Yes, 2's additive inverse is 4, and 4's additive inverse is 2, and 0's additive inverse is itself. And is it associative? Well, yes, it inherits that from Z6. So the subgroup generated by the element 2 is the 3-element set that has 0, 2, and 4 in it. All right, so we've got the subgroup generated by 2 mod 6, and I want to see how it connects to this definition and proposition. So let's think a little bit about what this proposition is actually saying. All right, G is a group, X is a non-empty subset, and I want to create a new set that has stuff in it based on whether X or the inverse of an element is in X. So H is going to be the set of finite products of x1 through xn, and the way that I decide which x's that I'm allowed to use is I either have to have each of these themselves is in X, or the inverse of the element is in X, and so I'm going to throw in, because this needs to form a group, if xi inverse is in X, xi will also have to be in H, or else we won't get a group. So what we're doing is we're saying that it's closed under products. That's because we're saying X is non-empty, so I should add that X is non-empty. So H is also not equal to the empty set. It's closed under products. It's going to be associative because G was associative, and this is a subset of G. It's going to have the identity E in there because if I have X in X, that implies that X inverse is in H, and so is X. And that means that it's closed under products, so X inverse will be the identity. And then our property that says if you have an element in H or in X, then you're going to throw it and its inverse into H gives us closed under inverses. And so we do have a group. And it's abelian if G is, and sometimes we get a subgroup of a non-abelian group that's also abelian, so this is not an only if. Our notation for the subgroup generated by the set X is S parentheses X in it. And the proposition up above says that actually S of X is the smallest subgroup of G that contains the set X. So it's the set generated by X, and it's also the smallest subgroup of G. Sorry, this is the subgroup generated by X, and it's the smallest subgroup of G that contains the set X. Okay, we're going to look at least one of these examples here. We're going to look at the example where we find the subgroup generated by 2 transpositions, or 2 cycles, in the group S4. Now, we are going to look for a candidate for this thing, and then we're going to make sure that it is actually a subgroup by checking its multiplication table. So that's what's going on in number 2 here. Our candidate is the set H that has the identity element in it, which I call E instead of iota because I have a hard time drawing an iota. We've also got 1, 2, which is its own inverse, so that's good, that's in there. We've got 3, 4, again, 2 cycles are their own inverses. And then we need finite products of 1, 2, and 3, 4. So we'll take the finite product. And if we kept adding 1, 2s or 3, 4s to the mix, they would simplify down to the identities. So I think that this is the subgroup generated by those two elements. And the way that I can check this is by checking the multiplication table to see that this is actually closed under the group operation, and then I can use one of my propositions about finite subgroups that says all I need to do is to make sure that it's closed under multiplication and under inverses. So we've got closed under multiplication. And in fact, I don't think we need to check inverses because we have a finite subgroup here. So it's closed under multiplication and non-empty. And that's enough for finite subgroups. The reason that's enough, just as a reminder, is that if you have a finite subgroup, then your inverse is going to be some product of multiple stuff in there, or else, you know, like if it wasn't, you'd have to keep adding stuff, and that would be a contradiction if we had to keep adding things. We could continue to do some more examples, and I will let you look at the next few on your own, so check these out. If you have any questions, you know where to put them. Slap them on Piazza. So Piazza is a great place for your questions. And I'm going to move on to the next slide here. It's kind of fun to notice that in this example, which I won't go through in detail, S of 2 in the group as a subgroup of the group of integers under addition. It doesn't have the little times decoration, so we know that 0 is included, which means it has to be a group under addition. It turns out that this is actually the principal ideal generated by 2 in the ring Z, which is a nice relationship and kind of a cool way of pulling together subgroups and ideals. So that's kind of fun. I like that connection. Now, there's something special about principal ideals, right? This is not just an ideal, but it's a principal ideal, meaning it's generated by a single element. And we're going to have a similar special name for groups or subgroups that are generated by a single element. Those are called cyclic. So a cyclic subgroup of G is a group that can be written. It's a subgroup H of G, where H really looks like the subgroup generated by a single element for some G and G, so for some little g. Now, that if I wrote down S of 2 up above, I might have written it as, you know, S of 2 looks like, you know, -4, -2, 0, 2, 4, dot, 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 some dot, dot, dots on this side. If I hadn't written down S of 2, you might not see right away that it's cyclic. But as long as we can write down S of 2, that means that because I have this single element that I can use to generate my group, it is a cyclic subgroup of the integers. So the existence of that element 2 means that this is a cyclic subgroup of Z. Now, what you might notice is that if I take any ideal in a principal ideal domain, under addition, that's going to give me a cyclic subgroup because the ideal under addition forms a nice little additive subgroup of our principal ideal domain. So we can find a lot of cyclic subgroups. We could go back and look at our examples of principal ideals. We could go into the field F bracket X and look for some ideals there, right? So if I is an ideal of F bracket X, then I is a cyclic subgroup of F bracket X, where the operation is addition, because we haven't thrown away our 0. So we've got an operation under addition. So that's pretty cool. And then the following text on the page over here just tells you about which of the examples before were cyclic, and the first one we looked at turns out is not a cyclic subgroup of S4 because you need two generators. You can't get away with just one. All right, here is one of the best theorems of the course, and we're going to use it later on. It says that if I have a transposition and an n cycle in S sub n, one of my permutation groups where I'm permuting S things, then I can write Sn as a subgroup of itself, which is allowed, that's generated by a 2 cycle, which we also call a transposition, and an n cycle. So the big takeaway from this proposition is that Sn is generated by a 2 cycle, AB, and any n cycle that have A and B next to it. And any n cycle, A, B, and then, C1 through, or I guess, let's say C3 through Cn. And there's a really nice proof of this in the notes. It goes through some of the details here, and I'm going to let you take a look at that. I think that's a good one for us to talk about in office hours if you have any questions. So part of your homework here is to glance through the proof and bring questions to office hours. Or, of course, you can use Piazza to record your questions. I think once you get the big picture of what's going on in this proof, you won't have too much trouble unraveling what's happening. Now, the star of our show later in the course is going to be the group S5. You might wonder what S5 has to do with anything, but remember that we're interested in a degree 5 polynomial that's not solvable by radicals. So I want a degree 5 p of x in q bracket x. And I know that if I look at the Galois group of the fixed field of p of x, the extension field with the roots of p of x in it over q, because that's degree 5, I have that crazy group homomorphism T that takes an automorphism to the way it permutes the 5 roots of that thing. And we know that T is 1-to-1. And so what we could say is that our Galois group, Q adjoin the roots of p of x over q, is isomorphic to a subgroup H of S5. So H is some subgroup of S5. Now, we're going to want to know whether or not that subgroup is all of S5. And one way to check is to use proposition 19.9. This says that S5 is generated by any transposition and any 5 cycle. So we know S5 is generated by AB and then any 5 cycle. It doesn't matter if A and B are next to each other or not. That has something to do with the fact that 5 is a prime number. We can talk about that a little bit. But once we have this, this is pretty good, because if we can show that one of the automorphisms in our Galois group gets sent to a 5 cycle and one of our automorphisms gets sent to a 2 cycle, that means that that subgroup H is all of S5, because now we've got a 2 cycle and a 5 cycle in the set that we're mapping to, and that's going to generate the whole group. So we're going to try to find an F that gets sent to a 2 cycle, and we're going to try to find a G that gets sent to a 5 cycle in the automorphism group, in the Galois group of Q join the roots of p of x over Q. And then we'll be able to say that the Galois group is isomorphic to S5, and that's going to be good news for a reason we'll talk about a little bit later in the course. All right, so take a an eyeball at that proof. Also notice that it doesn't work for S4. We could generalize. You could think about how you would generalize this to S sub p, where p is prime. And what goes wrong, you might notice, is that S4 is composite, and we have two disjoint 2 cycles here, and 2 times 2 is 4, right? So something about the fact that we're multiplying together 2 cycles and we can get the number 4 that way makes something go wrong. Of course, primes won't have that property. We won't have smaller numbers except for 1 that we could use to write down a product of cycles that would give us a 5 cycle or something like that, or a power of one of our 5 cycles. All right, so that's it for our chat about generators of subgroups. This is our Galois tie-in, which we are excited about because that's our ultimate goal. And I will see you in office hours soon. Hope everything is going well. Take it easy. Be well.